I wanted to be near this red layer here. And that's, you can explain it without it, but it really helps to be right there. One thing you'll notice, first of all, you've got this big hole here, which is called a sinkhole. The reason it's called that is because at one time this was solid limestone across here. An underground cavern formed underneath it, and as the cavern enlarged, pretty soon the ceiling wasn't strong enough to hold itself up, and it basically collapsed inward. It sunk inward and formed a basin. And for a long time it was standing water in here, and that's really the Bernie story about what accumulated in that hole. So they've gotten things back to about 9,000 or 10,000 years. That's probably just a little bit after the whole thing collapsed. That would be.
We're thinking about 7,000 years ago, the radiocarbon days.
Okay.
So we can go a little bit deeper than when we get the ceiling for another couple, 3,000 years.
You probably have caves up underneath there, you think?
Absolutely.
Yeah.
Absolutely.
Okay, so around 7,000 years this whole thing collapsed. Now, so that's timing of that event. If you date the limestones in here, we will probably get something between about 300 to 435,000 years old for the age of the limestone. That means that's when the limestone was actually forming, piling up here. And so that's the timing of the major feature. One of the things you can see prominently here is below this upper kind of flat-looking layer are some very highly inclined surfaces. Those are called crossbeds, or cross-bedding, and those are related. Whenever you see structures, there's always the back door out of things, but almost always it's related to wind-transported sediment, sand dunes. And generally, the sand is relatively well sorted. It's in a very narrow size range, things that can be carried by wind transportable size, and so on. But when a geologist sees that, the first thing you think of is ancient sand dunes, or sand dunes. And of course, in this case, it's rock, it's not sand. So something had to happen between the time that it was being blown and accumulating as a loose sand dune and it changing into rock. So that's another story. The other thing, the reason we came here, is that right at the top of that lower unit, there's a zone of red mudstone. It's highly calcareous, it's well cemented, but it's mainly silt and clay size material, and it's very red. So it's got a little bit different composition than the other rock. Now some of the other limestone is stained, but if you look at a fresh piece of it, that's pretty much the color of the rock. It's the reason it's got the reddish color on it is because it's stained with iron oxides coming over. And then above it is a thinner unit, which also has a lot of cross-bedding, just kind of smaller scale things. So there's actually two major units in here, and they differ in age by at least 120 or 130,000 years in age. And I'll just tell you to start off with that the geologic record here of the limestone actually is very closely related to sea level change over the last 435,000 years. So, as you know, with cycles of global climate heating and cooling, it's generally a cycle between about 100 to 125,000 years, depending upon who you believe and how accurate the data is. So as sea level's going up and down, the coast here is changing, and we're getting a different record of limestone accumulate. What's going on here? So that's how you kind of read this record. Now, let me go back to the very beginning of all this, and first of all, answer the question: why do we have so much limestone at this location? It's unique, but generally unique occurrences in geology is a combination of normal geologic processes in a unique combination, a unique setting, unusual setting. It's sort of like the green sand beach on the Big Island. That's all just normal sedimentology and volcanology, but it's the only one in the whole world, so things have to combine in a certain way. And the limestone here is the biggest development of limestone anywhere in the state of Hawaii, so there's something unusual about this location that provided for that. And this sinkhole is the biggest in the state of Hawaii, and the record in it is one of the best on the whole planet. So something, all these things had to combine in a strange way to produce this crazy place that we're at. But in Hawaii, this I'm going to go way back because the limestone actually starts with the lava rock. Any of you remember how much silica there is in lava rock in Hawaii? In the basalt, what's the percentage of silica? What? Well, I just wondered, because I don't know what level you've gone into this, but it turns out that that's probably the key starting point, all the way back to the origin of the volcanic mountain. The lavas in Hawaii are very low in silica, relatively. They rate about 50 to 52% of the rock is silicon oxide. If you do a chemical analysis of these rocks, and that's what most people do with rocks these days, they want to know the whole rock chemistry to determine its origin. Because, you know, earth science is nothing but looking at physics and chemistry and biology in terms of the combination of things. So start out with that. But that means that these lava rocks form, there's not enough silica left over after all the elements take up the silica to make their minerals, their feldspars and oxidites and whatever, all the different kind of minerals. There's no silica left over to make quartz, silicon SiO2. So that's, you know, quartz is one of the most durable minerals on the planet. Almost all of the beaches on the mainland, the west coast, east coast, is almost predominantly quartz sand. In Hawaii we have none. There's no quartz sand at all. So we wouldn't even have beaches here if it wasn't for probably the marine system that produces our reef system. And then the waves break those down and that they turn into sand grains, they end up on the shoreline. Just the right environment has the right hydraulics, the right energy for sand to accumulate at the shoreline. If it was finer than that, if it's silt and clay, it's going to float away. If it's coarser, it's going to end up alive somewhere else. So we have all these beaches around this volcanic mountain that are predominantly lime. They're made up of skeleton, mostly invertebrates, coral, mollusks, but actually, surprisingly, the predominant grain is a plant called coralline algae. It's a plant that makes the skeleton out of calcium carbonate. So you have calcite and aragonite carbonate available, and it turns out that that is tougher than the lava rock. I don't know if you've noticed or not, but there's hardly any volcanic beaches of sand on this island. There's only one, which is Waimea Sand Beach. I don't know if you've noticed that one or not there, but the sand that comes out of Waimea Canyon is there's so much there and it's so dry over there, you actually get a volcanic sand beach. It's the only one on the entire island, and almost 50% of the shoreline is a sandy beach around the island. So it turns out that chemically the lava rock is less stable than the lime. In other words, it breaks down chemically to silt and clay and then floats away. So it can't stay at the shoreline. Now, that's the first thing that amazed me when I got to Hawaii. It's like, it's a lava rock mountain. Why don't we have more lava rock beaches, or volcanic sand beaches? We don't. Now, of course, the Big Island is very young, so you have black sand and green sand and whatever. The true black sand beaches only form when the lava goes actually into the ocean and fragments. It's actually glass, it's not even crystalline. We have no black sand beaches on any of the other islands because that sand only lasts a short time. So that's the first thing. So we end up with a lot of carbonate sand on our shoreline. And then this island, this is a little physiographic map of Kauai to start with. As you probably know, the trade winds are very consistent in Hawaii, not as much as they used to be, but they blow in predominantly from the east and northeast, and this is the windward side of the island. And it turns out that this coastline right here, where we are, we're right down in here. This coastline is almost parallel to the average direction of the trade winds. And so the winds come right along that coast, kind of their maximum velocity. And because there's a bunch of steep cliffs along here, it's like a one-sided venturi tube. You compress the air and it actually picks up speed going along there. So it's almost always very windy on this coast. We always call it the glorious trade winds because it cleans everything out and it's just always gorgeous because of those winds. Well, any beaches that are accumulating along the shoreline, the wind has the opportunity to pick up the fine transportable size and move it down the coast and accumulate it in big sand dunes. And we'll see them later on today. We'll be with you. We'll see some modern sand dunes. So we've got the modern example there, and then we know that this has happened for a very, very long time. So that sand builds up on the coastline as large sand dunes. And all the relief you see here, and there's even a couple places that are as much as 80 feet above sea level, are accumulations of wind-blown sand. And they all have this high angle dipping, and they're all made up of lime sand. Now the thing with lime is it's not as stable chemically as quartz, so it starts dissolving a little bit and it cements itself. I think this rock has been compressed, so on to turn from sand to sandstone, or from lime sand to limestone, but it's been no compression here at all. It's all totally a cementation process. There's no compacting it down. And that gets into another, I'm going to go through these little scenarios here just to show you how complicated this maybe it is. I'm not trying to make it complicated, it's just to understand it, you got to look at all these details. And it turns out that because there's a mix of types of sand grains, from coral to coralline algae to clams and snails and echinoderms and all the stuff that makes skeletons, they have different chemistry. The coral is predominantly the mineral aragonite, which is calcium carbonate. It's a different crystal structure, so it's different than the mineral calcite, which is also calcium carbonate. Aragonite is less stable chemically than calcite. So when you accumulate it, and then you pile it up, and then you let fresh water seep down through it, the coral skeletons dissolve slightly. They release ions of calcium and carbonate that are then in the pore waters of the sand, and they start growing little crystals of calcite, which is the stable form. Those little crystals start growing around each grain, and they start locking together between the grains, and that forms the cement that glues everything together. So that happens, and that's why you change the lime sand to limestone. I might clarify the terminology a little bit there. Sedimentary rocks, and most rocks are classified by two major characteristics: texture and composition. Texture in sediments involves grain size, or angularity of the grain, or other aspects. And composition is the mineralogical composition, like calcite or aragonite. Sand is only a grain size term. It can be composed of anything. It ranges from up to 2 millimeters.